the logic itself is called non-axiomatic logic or now. So this is part of this, and also NARS is a formal language used by the system or the logic. Okay, so this is part of this. This is part of this. This thing also is built from layer 1 to layer 9 or level. Okay, whatever you call it. So what we have covered so far is only this part, right? And with its own language. So for the same reason, actually, I can also say that the language also consists of 9 layers, and the same thing can be said for the implementation. But just to avoid making things too complicated, usually I just call this NARS and call this NARS, even though you should understand there are actually different versions, including different functionality. Okay. So what I'm going to talk about today is how to implement this into a computer system. So clearly it's not the whole thing, but only the first layer. Okay. Later we're going to introduce more and more and more, but still the focus of this lecture will be on this part because we don't really have the time to talk about the whole system, and also this part is the most mature part of the project. Okay. But even though that's the case, I cannot only talk about this because otherwise most people will get confused. It doesn't make sense. So we will have to see how this kind of thing can be actually implemented in a computer system, which I explained before basically means to set up the proper memory structure and control mechanism for the system. So first, let's see. So far, what we have learned. Intuitively speaking, every NARS sentence is nothing but two terms or two concepts related by an inheritance relation with a truth value attached, right? So that's one of them. Then the whole system's knowledge base can be seen as a whole bunch of those things. Once again, as I said, is a directed weighted graph. Okay. And then that's the language part. And the semantics explains what those things means. And the inference rules tell you that each time, if you take this one and this one as a premise, what you can derive. If you take this one and this one as a premise, what you can derive. So each inference rule defines one single inference step. Okay. Typically, 2 premise, 1 conclusion. As I said, the conclusion itself will be added back into the graph, so the graph will grow. Clearly, the memory aspect is, if you really want to do it, not by pencil and paper, but by a computer system, you need to somehow store this into the memory. Okay. Clearly, you need more detail than just a weighted graph or directed graph. And also, the control aspect is, okay, this is the case. Currently, especially we are talking about AGI, right? So we should assume at least, for example, there may be, say, millions of nodes or concepts. Each of them may be related to thousands of other concepts. Okay? So logically speaking, especially according to the logic I introduced, there is many number of possible inference at any moment to be made, all following the logic. Okay? So you see that I can take this one, I can take this one, I can take this one. The only restriction as far as NAR 1 is concerned is this 2 things need to have a common node. That's the only restriction, logically speaking. Okay? But there are a couple of other details which we can ignore for now. But which one you want to do? Eventually, I assumed insufficient resource. You cannot just say do everything. You see that when I talk about the idealized version, I actually assumed to do everything, which is implied by the notion of transitive closure, right? Transitive closure in that context basically means to list all possible paths from one node to another and make a link, okay? And whenever you get a closure, that means you have exhausted all the possibility. In that logic, I can assume that because I ignore the resource restriction, as far as this is finite, that can always be done. In this logic, that's not possible anymore. Because at the very beginning, as I said, I set up the restriction that you're not allowed to assume the system can actually do everything. In reality, we know it cannot. Okay? So the central part of the control problem, simply speaking, is just this. In each moment, which node and which two link you pick to do inference. Or we can say that the logic we introduced last time defines the possibility. That is, what is the possible conclusion according to the given. Right? Some other conclusions are impossible, right, according to the given knowledge. But in reality, we don't really turn all this possibility into reality. We have to selectively do that. Okay? So the control mechanism is the one that decides which of the potential possibility will be actually realized by the system at the current moment. Okay? So now let's see. In a very general level, we say that there are a few extreme situation. Okay. One extreme situation I already mentioned is this one. If resource doesn't matter, you just do all of them. Okay. That is what I say, sufficient resource. Oh, by the way, please pay attention to the difference between these two words. Okay. Insufficient and finite. That's not the same thing. Okay. Many systems also say that you cannot assume infinite amount of resource. You have to say finite. But in my theory, actually insufficient is a stronger word than finite. Okay. It can be finite for many situations. This system is finite, but it's still sufficient, big enough for many of the problems. Okay. When I say insufficient is not enough. It's clearly finite, but furthermore, it's not enough for your problem. Okay? So just to say that transitive closure is finite is not enough. Even if that's the case, you still don't have the resource to try everything. Okay? So this approach is impossible. Even though people may say, oh, for a simple example like in your examples, clearly you can try everything, but that's not the typical situation. Okay? The control mechanism have to be designed according to a typical or normal situation for the system to work in, which is, number one rule, don't even think about trial possibility. Okay? Then there is also another situation, the other extreme. That is, okay, maybe your resource is limited, but you have perfect knowledge. In this case, we're talking about control knowledge. Here, control knowledge basically means what? Means that you kind of like know for a given problem what should be the best order of inference. Okay? To answer that question, you should actually take this and derive this. Then take this one, derive this one, and that's the answer you want. Okay? So if you know that, then also there is no problem, basically. You just use the best approach. Or it's kind of like, think this as a street map or city map, right? You want to go from this place to this place. If you already know the shortest path, then that's not a problem, you just take it. Okay? On the other hand, if you have all the time, then you just try all possibilities, then you can also get there. But both of them, according to my definition, doesn't require intelligence. Okay? The second situation, of course, if you know the shortest path, that's the best thing, right? But to me, that's a computation. Actually, according to my definition, computation is better than intelligence. It just, in many situations, computation is not available. You don't know that. On the other hand, of course, there is a third extreme situation. That is, you have no control information, no survival, whatever. You just have no idea. Okay, and if that's the case, also there is no smart thing to do. Okay, you cannot tell the difference between this path and this path. So for me, intelligence is really about the situation, which is kind of like between this three extreme cases. Okay, you have some control information, which means that if you are currently in this position, you do have some idea. Okay, maybe this path is closer than this one with respect to the final goal. But this knowledge is not absolutely certain. It can be wrong. Okay. So that's the situation I think the intelligence system like NARS should be able to deal with. Okay. So this idea, if I put it at this level, it's not new at all. It's there at the very beginning of AI. Okay? For example, heuristic search, many of you, I assume, are familiar with the concept. What they have is kind of like there is an evaluation function which make estimation about, from here, if you want to go there, if you don't, if you're not in any of that extreme situation, then you have some estimation provided by a function. Say that basically give each of them a score. Okay? Say this is maybe 5, this is maybe 4, this is maybe 6. Then let's say the smallest is better, then you take that's 4. Then here you do another evaluation among the options before you. Then you pick the best, right? That's the idea behind system like Deep Blue. So it plays chess according to a complicated evaluation function proposed by a whole bunch of chess masters. And they do it very fast. Each time they do the calculation and pick the best move. Okay. It's called heuristics because that kind of function doesn't guarantee to give you always the best move. But on the other hand, it's better than nothing. It's not a random choice. Okay. So that idea or something like that has been in AI from the very beginning. Clearly, it makes sense. But there are a lot of limitations. For example, especially for a general purpose system. Okay, you see that this basically means you may want to go from anywhere to anywhere else in this metaphor. Okay. So clearly, to make up a heuristic function for each task is impossible. Especially you see in AGI, according to at least in NARS, according to the open assumption, you don't really know all the problem you're going to run into. There is no way for you to prepare a heuristic function for each of the future tasks. Okay? So if we still use the heuristic search idea, that means that heuristic function itself must be able to be somehow derived by the system or learned by the system, rather than like Deep Blue is built in by the designer. Okay, that option is not available for us. So, yeah, roughly speaking, that's what I'm doing. Okay, so the system we already mentioned can build new links. Okay, that's basically the domain knowledge. Okay. You have some concepts, the relations among the concepts, which can be derived from given experience, but that's only part of the story. So beside the domain knowledge, the system should be able to learn control knowledge, which in this current form is not really in the map. Okay. It's kind of like additional stuff, which not only tell you what is kind of what, it also tell you that if you want to solve a certain problem, where to start, or which one to try first. Okay. So So the basic idea, I said, NARS is designed to be an adaptive system, which means it cannot expect the user to provide all the knowledge, all the control knowledge, and it has to learn by itself. Again, by adaptation in this context, it means sometimes you have to generalize the control information from its own experience, okay? Which can be wrong. Okay, because your experience is limited and biased, but that's quite normal as far as the system has the ability to correct the error whenever it gets counter evidence. Okay, so the spirit is similar to the logic part, okay, but the details, of course, are different. So another property of adaptive system is this. Again, the system learns from its experience. It also means the internal structure, if we also including the control mechanism into it, okay, it will change over time. Not only that, it will change over time in a certain unrepeatable manner. So that, for example, in theoretical computer science, we typically talk about automata or Turing machine, right? Which is a structure or a device with a set of internal state which change from one state to another according to the new information, and this is doing the same. But this have one additional restriction, that is, since it's adaptive, okay, every state will be different from its previous state. Or in other words, it never repeat a state. As soon as you add that into the picture, it changes a lot of things. Okay. First, I would say it's reasonable to assume that because think about us. Okay. We are getting older and older, whether you like it or not. There is no way for you to go back to one of your previous state accurately. Okay? Not only for us, that's the case for every adaptive system. So that raises a very interesting theoretical problem. That is this kind of system still a Turing machine? Who knows the formal definition of Turing machine here? Okay, not many. A common misunderstanding. Well, I assume you heard about this term, right? And it's a theoretical model of a computer. And many people will tell you, or if you read a textbook, it will tell you every computer is equivalent to a Turing machine. Okay, it's a theoretical model, which is true in a sense, but often misunderstood in another important sense. Accurately speaking, Turing machine is not a definition of a device. It's the definition of a process in a device. Okay. For those of you who know the concept, think about it. It's defined as some kind of mechanism with a certain state. Okay, it will change from one to another according to the input. Furthermore, in a deterministic way. Okay, so if you are in state 1 and if you see a 1, you go to state 2. If you see a 0, you go to state 3. Something like that. Okay, clearly a computer is just like that kind of thing. Nothing magical. Everything is predetermined in that sense. Okay? But there is one more thing that people tend to ignore. That is, Turing machine contains the definition of an initial state and a set of final state. Okay? Initial state is where problem solving starts, and final state is one of the states where you get the result. Okay? And one thing usually assumed, but almost never mentioned, is after you go to the final state, then what? Then the system reset and go back to the initial state, which is what gives you the notion of computation. Which means what? Which means if I always give you the same input in terms of a certain 0 or 1 sequence, the system will accurately produce the same output, right? Even if you don't know the notion of Turing machine, you know the concept of a program or algorithm, which is just like that. If you repeat the same input for the same algorithm, you always get the same result, unless there is a bug, right? Of course, some algorithm contain random number generator, which makes things a little bit more complicated, but the basic idea remains the same. Okay, so that raises a lot of theoretical issue, because traditionally people say because of that there is no way for computer to be creative. We have been talking about creativity, right? Why? Because everything follows a program, and the program is given to the computer by the designer. How can a computer be creative in the first place? So people say, okay, creativity must come from complexity or from random number, blah, 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 blah. That's possible, but there is actually a much easier or simpler explanation. That is, you don't go back. Okay? For an adaptive system, actually it's impossible to go back over time. Which means what? Which means, yes, there is an initial state when the system was born, right? And there is also a final state when the system died. But that's not the initial state and final state with respect to a problem-solving process. That's the life cycle of the system. Problem-solving cycle is much shorter than the life cycle. Problem-solving cycle in this picture does not have a fixed initial state anymore. Okay? Later I'm going to argue it doesn't even have a final state also. For example, I can ask you the same question at different moment. That means what? That means the state you get this question is not the same. Even if the system is completely deterministic, okay? Your processing and your answer can be different because you don't start at the same position. Especially because adaptive system can learn, okay? So if I repeat the same question second time, you already learned it in the first time. Typically, you give a better answer and you get the answer faster. I say typically. Okay? And also, even if the questions are different from each other, the second question's processing will depend on the first. We all have this experience, right? We will do homework after you learn a certain chapter. Usually a problem, if it shows up after a similar problem, is easier to be solved because you're ready for that kind of thing. You know where to go already. But if the same question comes to you in the middle of nowhere, it becomes harder, even though you have the same knowledge. Okay? So because of that, I have been keep saying that, which is misunderstood by many people, is in the problem-solving level or scale, a truly intelligent system does not follow algorithm. It does not use a fixed program. And there is no magic as far as you allow the system to grow and to accept problem at very different state. You don't always reset, go back to the original. Okay? Is this still a Turing machine? Again, yes and no. That's my typical answer, right, to many questions. If you check the whole life cycle of the system, you take that as the process, it's still a Turing machine. It's just like us. If somehow magically we get reborn with the same initial state, and the history also repeats itself, probably we are going to live the same life again. I don't know why it can be different. Okay? But in reality, of course, it doesn't happen. When we talk about a process, we're talking about a problem-solving process. That is, you give me a problem, I give you an answer. And that relation in this system is not a computation, not necessarily a computation. Of course, 1 plus 1 always equal to 2 in most of the case. But for more complicated problem, you cannot assume that anymore. And also, you cannot treat the input-output relation as a function anymore, mathematically speaking. Okay? Again, it will allow the system to be creative, to be original, okay? To take its own initiative with respect to problem. And you can give the system a problem without a predetermined algorithm, then the system can still process it. Okay? So this is probably the most theoretically important point behind the whole control mechanism of NARS. Okay. So what I suggest, and this is linked to a paper on that topic, is not traditional, one problem, one algorithm kind of thing, is what I call case-by-case problem solving. Okay. That is, even if the same problem is repeated each time or each problem case, it's handled differently because, again, those two terms. In each moment, the system's available knowledge and available resource are different. Here, furthermore, the knowledge also include the control knowledge. Okay? So the problem case may be handled differently, and in theory, you cannot assume it can be accurately repeated in the future. Okay? Then related to the issue that Chris have been talking about in the past days, time. Time has been to a large extent ignored in the notion of computation. Okay? Now we need to put it back into the notion of intelligence. Different moment, you give me the same problem, I may handle it differently. If you give a problem attached with a different time requirement, and also I need to handle it properly. Okay? So it's very often, later you will see in NARS, we can actually tell the system, work on this and tell me the answer very soon. Or work on this, you can take your time. It's not urgent. Well, of course, not in English, but in some kind of way. And in these two situations, you can expect the system to give you a different result. Okay? So in this sense, also, what is the computational complexity of the problem-solving process? Is it polynomial or exponential or is tractable or not? That concept doesn't even exist anymore. Why? Because the previous concept of computational complexity pre-assume you use the same method all the time, repeatedly. Okay? If that assumption doesn't hold anymore, the problem becomes the opposite. It's not the system tell you how much time it takes. It's you tell the system how much time you give it on this problem. Okay? Well, there's still simpler problems, more complicated problems. Of course, roughly speaking, you can still talk about complexity, but they will be fundamentally different from what the current computational complexity theory tell you. Because that kind of thing, you think about it, is based on repeated process. But in adaptive system, there is no repeated process in the problem-solving level. Okay? But of course, when you go deeper, you see, for an individual inference rule, like the deduction rule I mentioned yesterday, well, of course, it's still accurately repeatable and also is still carried out by an algorithm. No surprise there. Okay? So once again, I show you that when you observe or describe a system, a different level of abstraction, okay, you may get a very different conclusion. Many traditional confusing is caused by what? By mix them all together. Say, after all, your computer uses program, okay? Because of that, there is no way for it to be creative. Why? Because, yeah, in a certain level, you use program, but not at the problem-solving level. Okay? So we can talk about creativity. We can talk about how to solve. I have a paper just called How to Solve a Problem Without an Algorithm or Program. There is no contradiction. But when you check the internal structure of NARS, you see there's nothing but a whole bunch of programs, right? Of course. But those problems or programs are not defined with respect to user problems. So that's kind of like the most important point I want you to get. Okay, then if you say, oh, I still doubt how can you do that, but it kind of like makes sense. And then, okay, then we can continue to see how to actually do that using today's computer. I don't really think AI needs some fancy hardware like quantum computation or something like that. Today's computer. Okay. You just do it, use it in the right way. So, okay. Now we see that at the problem solving level, you have a problem, you're looking for a solution. But now you see that according to this analysis, you give up the idea about trying to looking for a fixed algorithm, take this as input, produce as output. Okay. Forget about that. Then how to solve it? Well, of course, once again, using the available knowledge and resource, right, roughly speaking. Then they clearly come from the second question. That is, we know is not enough. So that basically means for each problem, instead of trying to solve it completely or perfectly, you want to solve it using what you can afford at the current moment, which actually may change from time to time. Okay? So later we'll see that when I'm busy, okay, the same problem come in, I can still process it, but I only can afford a little bit of, a small amount of resource. When I have nothing else to do or someone somehow force me to work on it, okay, I will spend much more resource on it. So also, what if the system, also that's the topic touched yesterday, what if the system at the same moment have more than one goal to follow? Well, you do all of them. In which way? Well, whoever learned computer science know that time sharing, right? And like today's computer typically can run more than one program in parallel. And here, nothing special. I get that idea from my operating system course, but with a twist. Here the situation is much more complicated than that. Okay? The number of processes is much larger, and each process is not defined with respect to a given algorithm anymore. Okay? Which not only means it can follow different paths, it also means it can stop at a different position. It doesn't have, that's the thing I suggested before, it doesn't have a fixed final state for that process. Okay? Here we're not talking about the life of the system as a whole. For that process, it is like, if I ask you a question, how long are you going to think about it? Even I say I need the answer before the end of the lecture, that doesn't really give you an absolute deadline. Okay? Some of you will start thinking about that way earlier before that. And probably some of you will continue to think about it even after my deadline. Okay? So this concept is what I call, another phrase I made up, I call it controlled concurrency. Concurrency, basically means parallel processing. Okay? But this is very different from traditional parallel processing. That is, in my system, there is more than one goal to be reached, or in my terminology, I call it more than one task to be processed. So you can have, say, this is time. You can have this task, you have this task, you have this task, you have this task. And they kind of like being processed in parallel, but you don't want to treat them as equal. You cannot. Okay? So some of them will maybe go faster if it's urgent. Some of them may go slower. Some of them may go further. Some of them may stop earlier. Okay? Those of you who have learned operating system or some kind of like system course in computer science, implementation is not easy. So this is clearly implementable. Okay? It just very few system is designed in this way. Okay? So once again, I think most of the current limitation of computer or artificial intelligence is not caused by hardware. Many people say, well, now my architecture is bad. No. It's not designed for AI, of course. But it's not the bottleneck. The bottleneck is conceptual. You have used to use the computer in a very special way, and you think that's the only way to use it. That's the problem. Yeah? So, okay, here we say, basically what's going on is now, according to the basic assumption, it derived that now we want to give every problem a certain budget, which indicates the amount of resource I'm willing to spend on it. Okay? And that budget will decide. You see clearly here, since we have insufficient resource, there will be a resource computation among all the tasks. The general philosophy of the system design is to give everybody a little bit of resource, but not the same amount. Decided by the system according to several factors. Okay? And also, furthermore, the system will dynamically adjust this resource allocation according to the change of situation. Okay? So that's the idea. Now let's see. Okay, let's be more concrete. If that's the idea, then how to actually design a memory structure and control mechanism to support that? Again, we're not going to go into all the technical detail, but I will give you the key concept to the extent that I will estimate about half of the class. If you really want to do it, you should be able to code this all by yourself after the class, okay, to that level. Because the basic idea, as far as you accept my philosophical point I just made, the technical implementation actually is pretty simple. So what's the idea? The idea is here, you see, what you're doing is in each step, you're making a selection, right, among the concepts or nodes which way you want to work. And after that, on the node, you need to decide which two links you pick. That's what the control problem is about. So now you want to give each of them a chance, but also you want to prioritize the resource allocation. Then it's obvious the simplest solution is to give each of them a score, a priority value. That's exactly what I'm doing in the system. Okay? So beside the truth value, that's the separation. Don't confuse the truth value with the budget number. Okay? Truth is about evidence. Budget is about how much time you want to spend on this. Okay? They're related, but not the same thing at all. So, okay, now I gave each of them a priority value. And technically, I'm also using a real number in this range. But actually, in which range, later we'll see, it doesn't really matter because priority is completely defined relatively with respect to each other. Okay, how much resource do you get doesn't depend mainly on your score. It also depends on what the other people get. Okay, if you get a small one, everyone else get an even smaller one. You still get the biggest chunk within the system. Okay. So because of that, the accuracy once again is not very important here. Okay, you cannot ask me why is 0.5 is not 0.51. Well, it doesn't really make much difference. Okay. But intuitively, you can say, okay, we have a priority distribution among the nodes. Then what? Same idea. Within each node, each link will also have its priority distribution, priority value attached. Okay, so there will be some of you may say, oh, there are too many numbers. Yeah, I hope I use less, but it seems to be inevitable. If you have a better idea, then let me know. Okay, but anyway, that's the current design. So I also have this number attached, and then what? Then the process actually become pretty simple. In each working cycle, okay, and I will jump to this, and then we'll go back to the previous. This is the top level working cycle, which I have mentioned briefly in the first day. The system just repeated this, okay? As soon as you start it to run. It does what? It select a concept from the memory. And then it select a task from a concept and a belief from a concept. Both of them, roughly speaking, are just links. Okay, later I will explain more about what's the difference between task and belief. Anyway, you pick two links. And then what? Then you feed it to the inference engine, which will check all the rules. Okay, see which rule can apply. For example, if this is one, this is another one, and if you remember what I said last time, then you see it's a different, right? And X amplification, and you can use those two rules, and you get this two, and that's the result. And you put it into the buffer. Okay. Then you just repeat this process. But what I haven't explained is this keyword. You see, this is the whole control problem. Okay, how to select? Well, clearly now you can guess it's based on priority. But actually, at the very beginning, I think I could just use a priority queue, which means you pick the highest priority. But later I realized that's probably not the best thing to do. So later, the current design or the current implementation is selected probabilistically according to the priority distribution. What does that mean? That means everyone gets a chance. But if you have a higher priority, you get a higher chance. How to implement that? Actually very simple. I can tell you that's exactly how I coded this. Okay? Give you a simpler version. Let's say priority is a number, well, the real number is too complicated. Let's just say it's an integer between 1 and 5. Okay? Then what? In the system, if you check my source code, I have something like this. I have an array with a 1, 2, 2, 3, 3, 4, 4, 5, 5. Then I shuffle it. Okay? And then I treat this as a circle. That is, each time I reach the last one, I go back to the beginning. Okay? And then in the system, I build an array with my tasks linked at each level according to its priority value. Okay? So priority 1 things will be here, priority 5 things will be here. Then each time when I want to process the next one, I don't always take this. I take the index from this array. I take the next index from this array. Okay? Then I process things there. So in the long run, you will see this kind of task will be processed 5 times more as this guy's, right? Because it only get once after a certain period of time. Roughly speaking, that's how it's actually implemented. Okay? Of course, in reality, is actually my range is from 1 to 100. Later, we'll see in the demo. Okay. So that gives you a data structure, which I go back, which I call a bag, which is what is a probabilistic priority queue, okay? Which looks just like this. You see, this bag supports 3 major operations. One is you can put something into a bag, according to its priority value. Okay? If priority is 3, then new thing will be put here. Within the same level, you can just think it as a first in, first out, ordinary queue. Okay? It's very easy to do. The only additional thing for the put-in operation is every bag has a fixed size. Again, insufficient resource, right? Finite. Let's say this bag only contains 1,000 items, whatever it is. If it's already full, actually, in real situation for AGI, it will become full pretty soon. Okay? So normal situation, whenever you want to put something into it, you need to take something out of it. Which thing? Clearly, the thing at the bottom, with the lowest priority. Okay? You may still want to keep it, but I'm sorry, I have insufficient resource. Okay? Of course, when you have a bigger hardware, you can allow more, your bag become bigger, still is finite. No matter how big it is, okay, given the structure of this kind of system, it's going to become full pretty soon anyway. Okay. So that's the put-in operation. Then take-out operation is the most unique one. I just explained. You say, wherever you say you want to process the next one, which one? You throw a die. Okay, this is a die you throw. But it's not an even one. You get 5 much more often than 3 or 1. So whoever on top level will have a better chance in the long run. But typically, each of them in each cycle is only get a process a little bit, then it's going to be put back into the bag, waiting for its next run. Okay? So in each step, what you can do, well, for reasoning system is pretty natural. In each step, you just do one step of inference. So if a task needs to be processed or to be finished for a given problem according to a certain standard, for example, in 10 steps, how long will it take? It depends on its priority. Okay? So if it's here, usually it takes shorter time. If it's here, it may need to wait much longer because it has a low priority. Okay? So that's the idea. Also, of course, finally, we sometimes need to get something by its name. That is, you access it using a key. Okay? So because of that, actually, not only you have you see, this is what? This is an array of linked lists, right, in terms of data structure. Actually, this is combined with a hash table. The hash table, on the other hand, gave you the key reference mapping, so that if you just want something by its name, then the reference will tell you where it is. You can just directly take it out. Okay. So that's the 3 major operation in this data structure. That's the most unique data structure in the system, which is actually used in several places. You see that now you can see the memory is nothing but a bag of concepts. Each concept is a node, which is named by a term, right? So bird, for example, once again, refers to this one. But you should separate the bird as a name and the bird as a concept. Okay? Bird as a name is just a string. Right? Bird as a concept, it needs to contain all this information, which is a data structure. Okay? So the system is nothing but a bag of concepts. So that's why I said in the first step, you select a concept from the memory, because the memory is nothing but a bag of concept. Then within the bag of concept, within a single concept, there are 2 bags. One is what I call task. One is what I call belief. Roughly speaking, task is what you problem you want to solve about that thing. Belief is your background knowledge about that thing. Okay? So basically, you see, in this system, there are actually two types of tasks. There are two types of tasks correspond to what? To the two types of sentence. We already mentioned, it can be a judgment, meaning that I know this is the case to this degree. That's called a judgment. Okay? Technically, again, the terminology. This is a term. This is a term. This is a statement. A statement plus a truth value is called a judgment. Okay, which indicate to what degree the system believes this. This is one type of sentence. Another type of sentence is a question, which technically is a statement without a truth value. Okay? You want to know whether the bird can fly or whether the bird is a type of animal for some reason. And especially, of course, in a question, some of them can also be what, right? It's a variable to be instantiated. Later you will see in the example I use something like this. It's a name start with a question mark. Okay, that's just like what or which. Okay. Anyway, now we have two types of tasks. To process them means what? To process a new judgment means I'm learning a new knowledge, but not like traditional database or knowledge system. It's not merely put into the corresponding bags. Okay, it will be done in that way, but not merely that. Furthermore, it's going to be used to do forward inference with the related knowledge. It's kind of like I tell you something, you don't just merely literally remember it. You also think about what it means by combining that with what you already know about the related stuff. Okay? So that's why when you tell the system something, it will spontaneously begin to do inference on the thing by combining it with, for example, this and this. Or of course, it need to be related to it. Okay? So that's one type of task. Another type of task, of course, is a question. It's kind of like a query. Okay? So I'm asking you whether there is a relation between S to P or what's the truth value about that. Okay? Then, if of course it can use the name to identify where it's stored. But be careful. It's not a simple query. Say, oh, is there a link? What's the truth value? Because this truth value very often or usually doesn't really summarize all relevant relevant evidence with respect to that question. It summarizes some of them. Why? Because we already assumed, okay, this is not necessarily derived from everything else taken into consideration. The system doesn't have the resource. Okay. So even if you ask for this, then there is already such a link. That's kind of like your first response. Okay. Or people say, that's my intuition. Yeah, I think it's true. But if you think more, you may say, oh, no. I also, if I take this into consideration, I derive another one which can be merged with this with a revision rule, I get a different answer. Okay. So anyway, when the system gets a question, it may trigger backward inference. It may trigger some other things to be taken into consideration to get an answer. Okay. So anyway, now we have two types of tasks to be processed. Okay. And then we also have belief. That's kind of like the background thing which is waiting for the system to use. Okay. So roughly speaking, you see that we can say that there are two types of links. The task is kind of like the active link. Okay. that need to be processed. And the belief, on the other hand, is kind of a passive link. It's waiting to be used. So whenever you do an inference, not only also always take two links, it's always one task, one belief. And this thing also makes the control mechanism much easier. Okay, if you say any two beliefs can be used to derive new things, there is way more possibility to be taken into consideration. And also, typically, the task bed is much smaller compared to the belief bed. For example, for bird, you may know, say, 3,000 of relations which are all here, but you only think about one of them or two of them which are here. Okay? So that's kind of like a technical distinction, but it has some important implication. Okay, now I think we are pretty clear about the overall process. Okay? So the memory structure is a two-level hierarchy. On top level is nothing but a bag of concept. Each time you pick one. A concept is a data structure which contains two bags within, which is a task bag, smaller, and belief bag, bigger. Okay? Then each time, if a concept is selected, it randomly pick a task, but here randomly means biased by the priority value, and a belief, and do the inference, which can be forward inference if this task is a judgment, or backward inference if this task is a question, okay? Which will derive new questions. And also, if this task and this belief happen to match each other, and this one, if this one is a question, then this one provides an answer. Will the system report all the answers? No. It will always only report the best answer it found so far. So how to judge the quality of answer? What is the best answer? That's the choice rule I mentioned yesterday. Okay? If for the same question you have more than one candidate, then if there is no test variable within it, you just pick the highest confidence value. If there is a variable to be instantiated, you pick the highest expectation value, which I explained last time. Okay? So what if this one and this one match each other, but this is a judgment? Then in that case, what you do is a revision rule. It's kind of like for the same thing you have, now you have two different opinions. If they can be combined, you combine them together by merging the evidence pool. Okay? The question is whether I have an algorithm to select this. Yes, I do have an algorithm. The algorithm is exactly the one I mentioned. When I take out something out of a bag, there is an algorithm which will make the decision according to the priority distribution. Okay. So you'll see that, again, go back to the original problem is every step is controlled, of course, by an algorithm. It's just how those algorithms are combined together to solve one given problem that change from case to case. Okay. It's kind of like, yeah, all the building blocks are fixed, but how to combine them to make a new house, it changes from situation to situation. But whenever we talk about problem solving, we're talking about the house. We're not talking about a single block. Okay? It's in that sense I say there is no algorithm. That's the gap. But for this, of course, otherwise how can you justify it? Actually, that's what I mentioned in the first day, why I want to use reasoning system in the first place. That is, every step is well defined. Every block is solid. But how to combine them to build, to get a building, it's completely up to you. Okay? So you see, I can do a deduction followed by induction, followed by revision, followed by abduction. No problem. I don't have to have an algorithm say number one step have to be deduction, then followed by. I don't have an algorithm at that level. Okay. Question?
Could you please repeat the definition of concept and what does it include?
A concept is a data structure which is named by a term. It includes all the tasks and beliefs that directly use that term as a subject or predicate. Okay? For example, if I have a sentence, say bird is a type of animal. This sentence is stored or referred by the bird concept and the animal concept, and have no direct relation with the table concept. Okay? So that corresponds to, you see, that's why I said this is a concept, this is another one. So, for every question, the system only reports the best answer it finds so far, and also, of course, it needs to remember that answer. Okay? Just say that you ask me whether a bird flies. Somehow, I already have a link there. Say that bird flies, the frequency is 0.9, confidence is 0.4. I will tell you right away that I think it happens. But if I continue to think about it, I may say, okay, because of this and this, I make this one stronger. I say, oh no, later I will say, no, it's not just 0.4, maybe it's 0.7. Because I have new evidence taken into consideration. This in artificial intelligence is a concept developed a couple of decades ago called anytime algorithm. It's similar to that, which is not like traditional algorithm, which has a predetermined beginning and end. Anytime algorithm is still an algorithm, but it can, in principle, stop anywhere in the process. Provide a better and better and better and better answer. What it does basically is incremental improvement of the solution's quality. Okay. So what makes it better is much more flexible in traditional algorithm. It does not have a predetermined computational time anymore. It depends on how much time you allow it to run. Okay. So in that sense, my design is similar to anytime algorithm, but it goes even further because, as I said, it's not even an algorithm in the first place. It doesn't even follow a predetermined sequence of steps, but it's similar to algorithm. Anytime algorithm in the sense that you can stop it when you run out. You don't have to wait for a certain amount of steps. Okay. So basically, the system for a question will just say that I'm going to think about it. When I get an answer, I will let you know. But I will continue to think about it. If I get a better answer, I will change my mind and say, sorry, this is better. So if that's the case, in what situation the system eventually stops thinking about this process? Of course, there will be a stop. Okay? It's not determined, typically it's not determined by a logical standard. It's not because I say, well, many AI systems do similar things, but they stop by a logical standard, meaning that, for example, if my confidence rate 0.8, that's good enough, I will stop. That's kind of like Herbert Simon's idea. Okay? You decide a level of satisfaction, then you stop right there. That's better than stop at the end, but still not good enough, because this level of satisfaction is fixed. Okay? You see, in this situation, when you stop when you don't have time for it. In this structure. When this thing is pushed out of the bag by the other tasks. In everyday English, when do you stop thinking about something? It's because you have more important things to think about. It's usually not because you know you cannot get a better answer, or you're absolutely happy about your current answer. No. It's about you running out of time. You have better things to think about. Yeah.
But if you're somewhat satisfied with your answer, it can decrease the priority of the...
That's exactly here. After each step, clearly the priority needs to be adjusted. Okay? So for every question, if I get an answer, yes, the priority typically get decreased because you are somewhat satisfied. Okay? It's better to use the time on something else. But if you don't have anything else, or if this problem is really, really important, you may continue to think about it. Okay? So you see, that's why everything depends. Not only depending on this problem, it's also depending on the processing context, meaning that who else are there, who compete with me, okay, for resource. So the behavior becomes highly context sensitive. That's why I said if you repeat the same question at a different moment, typically you get a different answer. Why? Because the priority distribution change. Okay? Another thing I haven't mentioned, what we just said is task. Okay? A task, if you get answer, priority get lower. Another thing over the board is in every bag, there is that universal decay process of priority. That's the forgetting mechanism we're familiar with. Okay? All the priority values become lower and lower and lower and lower over time, under the assumption that for an adaptive system, the current situation is more important than something happened in the past. Okay. So that's another factor that contributes to the dynamic resource distribution. And so that's another thing that gets adjusted. Also, for example, beliefs. For bird, I know 1 million things, or 3,000 things. Which one should I think about first? If I cannot think about all of them. Well, it depends on several factors. One factor I want to mention here is the usefulness in the past. Okay? If I ask the system a question, and one of the beliefs provide a pretty good answer, then what? Then the priority of the task get decreased, and priority of the belief get increased. It's reward and punishment. Okay. So in the long run, not necessarily in the beginning, of course, in the long run, all the beliefs will be prioritized. So whenever you mention a concept, the most useful thing will be recalled sooner. Okay? That's something have been well established long ago in psychology, right, about human memory. So forgetting typically is taken to be a bad thing. But in this picture you see it's absolutely necessary. Okay? Because it's basically a prioritizing mechanism. It will make mistakes, but it's still better than without such a mechanism. Then you will have to treat everything as the same. You have to go through everything, which you don't have the time. Okay? And randomly pick things, of course, is even worse. Okay? So you see that there will be a lot of details, but if you understand this overall idea, as I said, according to your training in computer science, I will expect at least half of the class should be able to just design this all by yourself. Of course, your result will be different from mine, but this idea is actually pretty easy to get. Okay? You just ask yourself, how should I prioritize the belief? Well, as I said here, or a concept or a task. In all these three situations, there are three major factors. Maybe more, but so far I think there are three major factors. First one is quality. That is, you can evaluate the priority according to the internal property of that data item itself. For example, if we are talking about a belief, everything else being the same, a judgment with a high confidence should have a higher priority than a judgment with a low confidence, of course. Right? And this is better supported by history, and the other guy is just a pure guess. it's not very likely to be very useful. Okay. So this is one factor. And also, for example, for concepts, you see, if a concept have a lot of strong links, meaning that very stable link with other concepts, then that concept itself have a higher quality than another one which you just heard someone mention, but you have no idea what that means. Right? Then, this is what I have said before. It's performance record. That is usefulness in the history. You get that number by doing a sequence of reward and punishment. Any single case doesn't really mean much. Okay, a certain, you see, especially you be careful. Okay, truth value will influence the quality, but is not directly related or always related to usefulness. Everything else being the same, yeah, I said high confidence things are better. And also, for frequency, for confidence, we want it to be higher. For frequency, it doesn't necessarily to be higher. Typically, we want the frequency to be more extreme. That is, to be closer either to 1 or to 0. You tell me yes or no. Okay. If it's always in between, it's not going to contribute much for my decision making in the future. Okay. So you see, in this sense, you can also take many other things into consideration. For example, the simplicity of the concept, which we are going to talk about in the future. In level 1, everyone is just a word. It's equally simple. Okay. But if it's a phrase, if it's a sentence itself, of course, you prefer a simpler one. That's another factor. You see, in this situation, there are many factors to be taken into consideration, and none of them will decide all by itself the final score. Okay, some kind of balance or compromise of the things. And the truth value is not everything. Okay. For example, I can say that this table is an object. Well, this statement will have a very high truth value. Okay, there is no way for you to argue for that. But this thing is not very useful, except as an example in my lecture. Okay, otherwise you're not going to think about this relationship. Okay. So you see, this are kind of like two independent dimensions when you evaluate the priority, and finally, whether it's related to the current moment or not. There are a lot of very useful knowledge in your mind, but you don't have it in your foreground. It's more in your background at the current moment because we're not talking about those things. Okay. So how to achieve that? You see, if I give the system a new task, and put it, for example, now I'm asking you, whether a bird can fly. And that task will be put into the bird concept and the fly concept. At the same moment, it will activate the two, will increase their priority value because they are relevant to the current situation. And then also by inference, their neighbors will also be gradually activated, more or less. So in this sense, it's kind of like activation spreading in neural network, even though the detailed mechanisms are different. Okay. So, or in psychology term, the last one is more related to short-term memory. The first one is more like long-term memory. And the middle one is kind of like in between. Okay. It's accumulating short-term evaluations into something that will work for the long. So each of them itself also can be evaluated from a different angle. So this evaluation function can be complicated, and also it's pretty hard to say what is the optimum function. Okay? But at least it gives some idea for us to start with, which is good enough. So you see, now we basically have the whole picture in informal manner. Now you should be able to run this thing in your mind, okay, following this. Okay. You see that each time we get something, and pick something, and using this algorithm which prioritize things, and pick one that high priority thing get a better chance. By the way, this idea also is related to evolutionary computation, like genetic algorithm, blah, 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 right? Resource computation. And then you do inference, and you get some result. You put the result into the buffer, and also you adjust the priority. By the way, of course, there's no way for you to adjust the priority of everything that's too big, okay? You just adjust the priority of the item you have used in this process. Okay? And we have a more indirect way to handle this over the broad decay. You don't really want to, every cycle you go through everything. You don't have to do that, okay, to have an overall decay. It's just whenever you pick something and you decay its priority according to how long it has been accessed from the previous time, something like that. Okay, so it can be done. So the interesting property is, you see, if you understand what's going on here, you will see this whole working cycle basically take a constant time. It doesn't have anything to do with how big the bag is. That's very important. Okay. So how much time you're going to spend on each problem? Well, depends on how many steps is allocated to it. Okay. Each step takes more or less a constant time, and if you get processed more often or more times allocated to it, it will be interact with more belief. Typically, you have a better answer. But of course, it's not guaranteed. Well, nothing is guaranteed. Okay? It's possible that this problem can be solved by and only by this belief. It's just for some reason, this is just unlucky. Okay, that thing have a high priority, but you haven't picked it for a while. It happened to us all the time. My conclusion is, unfortunately, that's inevitable. Okay? Just like we often forget important things, that's inevitable. It's better than no forgetting. Okay? So once again, my excuse is, as I said at the very beginning, disclaimer, right? I'm not after absolute optimum. I would just say this kind of system is the only way, as far as I know, for a system to work with insufficient knowledge and resource. Okay? So, yeah, and then you add the derived task, input task back. If we go back to this picture, where is that link? I show you the system architecture before. Okay. Now you should be able to have a better idea about what it means. Let's go here. Now you understand this, and this is carried out just in that way. Okay? That's how you select something to be put into the system and to be taken for inference and so on. So that's the conceptual structure. Then, any question? Short question.
Back to my previous question. For one concept, in the belief and task belief, it's only about the terms have a direct relationship?
Yes, only direct relationship.
So my real question is, if you have a problem to solve, more complicated, there might be
multiple step, chain reaction.
So you will divide it into several steps.
Yes. Well, that's backward inference, right? This question will trigger a sub-question, maybe more than one sub-question, and each of them will be sent to different concepts to solve, and all the answers will naturally go back and which will trigger forward inference, eventually solve a final problem.
So, theoretically, maybe you are basically.
Not only theoretically, later I will show you an example. Okay?
My question is, if when you're how to say the smallest unit of steps is based on this term between term, and how can you consider it as a function step?
I think the best way to answer that question is after the break, I'm going to just show you the code and run the demo, and we'll go through several examples, okay, which may answer this kind of question better than this picture. This is too brief.
Is this control knowledge stored in the memory?
Yes. Yeah. Again, you're going to see it.
Okay.
Okay, let's take a break until 10:10. Of the system. First, all the implementation related information are here. Once again, you go to my homepage. Then there is a link under research called demonstrations, and these are all my papers, right? I mentioned before, a whole bunch of them. This gave you all the links to all the stuff I'm going to talk about today. So there are actually, I have implemented this several times in different scale, different version. Currently, I'm keeping 2 implementations. Okay. This is kind of like the major one. It's in Java. Now it become open source. I'm going to say more about that later. Also, I want to briefly mention that also I have Prolog implementation, but only the logic part. Okay. Also have source code. Anyone know Prolog here? Okay. Yeah, I like it. I still like it, but it just you just cannot use it to do the whole thing. Okay, use it for the control and memory is frustrating. But the inference rules is much more clear right in Prolog if you want to take a look. And this is the system, the free software I use to test that. Also, if you only are interested, or for something you just want to use pencil and paper to go through some example, actually the easiest thing to use is to use this spreadsheet, which contains all the truth value functions. Okay? All the formulas are here. You'll see that, for example, all the inference rules, you can specify the frequency and the confidence of the 2 numbers, and then you will see that what will be the result of each of the inference rules, inference truth value function. So that you don't have to really run the program to do some simple example. So I'm not going to say too much about this. So I have this 3 things. The major stuff, of course, is the Java implementation, which is here. All the source code are online here, but I do not encourage you to take a look at the code. Okay, it's way too complicated for beginners. But I strongly encourage you to try the demo and play with the examples. Okay? And then if you know it well enough, then you go to, no matter how good you are in Java, okay, that actually doesn't matter too much. It's the conceptual, the design principle you have already seen. It's very different from a traditional program. Okay? So this is the open source, and the source code, the current source code is here. Just in case some of you have to take a look, okay? For example, all the inference rules are defined in this class, and this is the language specification, and so on. Okay? And for example, the back data structure is coded here, okay? Just to show you I really have the code, okay? Not pretend. So what you really want to do, Here, the current version, this one actually just get uploaded this morning, is not a complete implementation of the logic. As I said, the control part is much less mature than the logic part. The logic part in my recent book, I actually have a complete description about all the 9 levels, even though some of the details still need to be decided later. But the big picture is already there. That's more or less complete. For control, now you'll see that this version only implemented up to level 6. Actually, I have a previous version implement all the way to level 9, but it became a mess. I'm not happy about that at all, so I take it off and try to restart from a better design foundation. So currently in the current version, I have all the way to level 6. Now you still have no idea what that means, right? Next week, we're going to say beyond level 1, what each level will add. So here, you just know that it's not the whole thing. Okay? We don't have the whole thing yet, but it will be good enough for this implementation, for this lecture. And also, that also means that in the following, what I just told you before, actually speaking, is not true. Okay, and that is an implementation of layer 1 only. The real thing is much more complicated than that because of the additional layers. Okay. Unfortunately, currently I don't have an implementation of layer 1 only, okay? Even though that thing can be done according to what I just said before. So if later we're going to see something that doesn't consist with what I told you before, that's the reason, because we need additional complexity to handle the other layers. So how to write this? This thing is built both as an applet and application. Okay. The applet version, you can just directly click this. If your browser support applet, it will start to run. But it has limited functionality because applet cannot access files. Okay. So a better way to do is just to download a jar file, which is the application version with full functionality. It's pretty small. Since I already have it here, I can show you that one. And those of you with your laptop with you, you can directly try it. As soon as you start the application, you will see automatically 2 windows. Okay. And this is the input window. That's how you tell the system new things. And this is the main window, which gives you all the control, as well as in this area, it will show what I call the experience of the system, or basically the history of the communication between the system and the user. Okay. And there's also a couple of buttons control the system. And we're going to do some demo later, but I will show you the first, the overall structure of this website and what other information you can have. Okay. And this is where to get the executable, and this is where to access the source code if you really want. Also in this website, I also have a bunch of wiki page, which will help you, especially this one. Where is that one? Input-output format. This page explains the grammar, which is the same grammar as in the book, but in here you'll see that the ASCII code doesn't include all the symbols, so that I'll tell you which symbol is which concept. Okay? So you can map this with the book. For example, the inheritance relation in the demo is represented by 3 characters. Be careful, okay? If you miss one, you don't get it right, and so on. Okay, so this is the full grammar, which of course you can see is more complicated than what we have covered only for layer 1. Okay. For layer 1, you just have an inheritance relation between 2 terms which are nothing but a word. Okay. But anyway, this is the grammar with some explanation. And also, this page is also interesting. It's not here. Yeah, that's the one I just showed you. And this one also gave you explanation about the GUI. Okay. How many windows are there, what you can do on each window, blah, 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 blah. Very brief description about how to use this demo. Then what? Some of those files are prepared by my former students at Temple who have tried to use this different domain to a different level of complexity. But what I suggest you to try are these two links. Okay? This link to the page where I explain so-called single-step inference. Okay. Just as I said, you see, when the system runs, it repeatedly do inference. The simplest way to understand it is to do one step at a time, right? So each step, you give it some input, and it will produce some output. Okay. This page gives you an explanation about how to understand this format and what those special symbols mean. Okay. Roughly speaking, let's see. Every line starts with asterisk or this small star will reset the memory to empty. Okay. Everything in the following is basically comments, and just with some additional information. A single character is enough to erase everything in the memory. Okay. So the system typically starts with an empty memory. Then, as you can guess, this is the input line. This is the output line. This is an inheritance relation, okay, with subject, copular, and predicate, surrounded by this pair of angle parentheses or bracket. This is clearly the truth value. Also, yeah, there is a punctuation which we are going to introduce in the future, but now you can guess. This means judgment, right? The dot means it's a declarative sentence. This is the case. And then if it's a question, then it will be a question mark. Later we will see that. And these two numbers are the truth value. Again, the first one is the frequency. The second one is the confidence. For input lines, they are both optional. Okay? If you don't say anything, you just say this. That's good enough for the system. Okay? Then what the system will use is the default value. Okay. You see, the simplest way to play with it is just use copy and paste in the input. Okay. Each line will be interpreted as a separate sentence. So this is the simplest case. And you see, okay, it will be added into the system. So this part is display only. Okay, this part is the area you can edit. Okay. So you'll see that you get an input line with this content, and this, now you see, is the default value, default truth value. If you don't say anything but period, it's assumed it's positive, it's affirmative. And the default value is 0.9. Okay, that's the convention. If you have a stronger belief, or for example, if you say it's not 1.9, but something else, of course, you can just change that. Okay? And also, especially if you only provide one number, that's also allowed. Later we'll see some examples contains that. It will be interpreted as the first number. That's the frequency number. Okay? The confidence number will be, again, the default. So if you want to put in a negative sentence, for example, if you want to say bird is not swimmers, of course, that just, you can simply do this. Okay? That will be a negative thing. And what are these? The following numbers are used for basically a debugging purpose. Okay? this is time. The first number is at which moment that thing get into the system. You see there is a system clock. Okay, initialized to moment 0. And then the second one, as you can guess, is the serial number of input lines. So this is line number 1, number 2, number 3, number 4. Okay. So in this case, I'm putting 4 things at the same moment into the system. Okay. Then some other things you can do is you can put in a single number, which basically means you allow the system to carry out 2 working cycles according to the process I explained before. Okay. This is how you allow the system to think longer or shorter, that kind of thing. Equivalently, you can click this. That's one step, another step, another step. Okay. This is the overall time. This is the time between the previous line and the current moment. Okay. So you'll see that in this case, you can see, after you get in the system, do 1 cycle and produce something, and do another cycle, produce something. Okay. And then you see 4 more cycles, there's nothing produced. And if you continue, maybe sometimes the future time it will produce something else. Okay. It may or may not happen depending on the input. And also, now you can also see, this indicates this is generated at moment 1, according to the system clock. This tells you now where it comes from. Okay? So this is derived from the first line and the second line. And clearly here you can see it's a revision. It's kind of like merged together. And this one is from the first line and the third line. And eventually this one is from line number 1, 4, and 2, and something like that. Okay? But this record is a partial record. It doesn't remember everything. It remembers kind of like up to a certain number of steps. Okay? Because again, finite amount of resource will be used to keep this kind of history. So the system is kind of like, if you get an answer, if you ask it, where did that come from? It has some idea, you see. But it's not necessarily a full, complete, accurate record. Another thing this is used for, this is what we call evidential base. Okay, that's kind of like which evidence is used to get the conclusion. And each input itself is taken to be a piece of evidence by itself. Then everything else derived will be the combination of the evidence of its parents or the premise it used. And this is also used for the thing I mentioned last time, yesterday. That is, when you merge 2 things, you don't allow overlapping evidence, right? Otherwise, you're going to count something more than once, which is not allowed. How that's implemented? Well, simply check whether their evidential base have overlap or not. Another thing I didn't mention is similarly, not only for revision, okay? You see, I already talked about this triangle shape. If you have A, B, C, you have this link and this link, then you produce this link, okay? But if you don't have any control, you see, it's a disaster, because this link and this link together will produce this link, which will be merged with the original one, and this one, once again, with this, it's an infinite loop. Clearly, you don't want that to happen. Again, I'm using this simple algorithm to prevent that from happening. Okay? So you see, if this is 1, this is 2, and the evidential base of this will be 1 and 2, and this will prevent it from being used with this again, because they're based on overlapping evidence. So that is not only a restriction for revision, it's actually a restriction for all the inferences, so that you're not going to actually have a loop. Even though theoretically speaking, if you don't think about that, all of them are allowed by the logic. Okay? So that's what those things means. Then what else we can say? That's basically it. Okay, here I have a longer explanation you can read. Let's see, the other buttons. This one, for complicated problem, of course you don't want to type every character one by one. So it will actually, at least the application version, applied version doesn't allow you to do that. Okay. Application version allow you to load a pre-edited file, just as if you're doing copy and paste. Okay, which will run continuously in the system. Okay. Which will make things, of course, much more complicated. And also, this is a symmetric operation which will allow you to record one of your dialogue with the system into a file which can be loaded back in the future. So when you're doing some experiment with the system, you can kind of like start a recorder, and this way will remember everything to a file you specified. Okay, which you can analyze in the future. So that's another function. And you see this color indicates whether it's under recording or it's done. Okay? You switch between two different colors. And also, it can also record the inference process, which I will explain later what that means, okay, into a file, which again for debugging purpose. And this will reset the memory back to empty. Okay, I will indicate that here. And also, it should be implemented in the future. That is, we don't have it yet, okay, but it will definitely need it to store the current memory state into some kind of database or file, so that you can load it back in the future to continue the processing. Okay, currently it's just very simple. Each time you restart from beginning. Okay? But that clearly can be done. It's just a matter of work. And this other interesting stuff which allow you to look into the system or the memory. Okay, let's see if we use. And by the way, all the examples are here. All the single step examples. Here you see it's organized according to the layer. Okay, so here you have everything from layer 1 to layer 6 plus two special files, which I will explain later. For each layer, I actually have two files. Okay, one is unedited, one is edited. You see, the unedited is the real thing. It's the real input-output communication between the system and the user. And the edited version will just simply manually edited some of the detail. Why? Because the edited version will allow you to only concentrate on one layer. But in the implementation, I already said that before. In the implementation, in this version, for example, layer 1 to layer 6, all the rules are all mixed together. Okay, you don't really have a separation there. So at the very beginning, I will suggest you to use this one, to use the edited version, so that, for example, for layer 1, everything else will be removed. And also this come with the English translations, which roughly tell you what each sentence means. Okay. The other one is automatically produced by the system. It doesn't contain any additional information. And everything starts with this // of course, the comments, which are here, English translations. Okay. So it will help you to understand what's going on here. So, for example, this will be, if you want to try this example, what you want to do is, you can just copy and paste the whole thing, or actually speaking, in this case, you only need actually this line and this line. Okay? But it doesn't matter if you copy the whole thing, because everything starts with double slash or with the output will be ignored by the system anyway. Okay? So it doesn't matter. Just to make things simple, you just do this, and the system will produce the result like that. Okay, let's do something more interesting. Well, single step is kind of boring. There's nothing very interesting. Okay, you see the reality. If you actually do this, you see It actually produces more than what I have mentioned here because there's more than one rule is actually used. Okay? But here under deduction, I remove the other rule. Just say this is the result produced by the deduction rule. Okay? So that makes make you understand it better. So then what you can see under this view menu, you can see this is exactly the concept bag I have been talking about. Okay, you see currently within the system there are actually 5 concepts, and these are the 3 you can expect. Okay, that's because the input is a bird is a kind of animal, robin is a kind of bird. Clearly there is a bird, there is an animal, there is a robin. But accurately speaking, there is also a concept which takes the whole relationship into consideration as one. Okay, but that's something we haven't mentioned. That's going to be introduced in level 5. Okay, that is actually every link is also treated as a node. That's why I said the picture I show you is a highly simplified version. The reality is much more complicated than that. Okay? But if you only want to do level 1 inference, you can ignore that. Also here, there is some control which will allow you to only show part of, typically only the top of the bag. Because in reality, if you have a big example, there's way too many things. Okay? You may only want to see the peak of the iceberg, right? You put everything under the surface, invisible. So the number of levels, as I said, is from 0 to 100. Accurately speaking, is actually the priority value is always between 0 and 1. Okay. Then in the system, I just move the decimal point to place. So if the priority value is roughly here, then you are going to see it on level 55. Okay? Just to make things simple. Okay. So you'll see now here. You see that's why the priority value is somewhere in this range. Okay. And this is kind of like in this range. And if you move it to a higher level, then you don't see anything below it and make the display looks better. You just only show more active things. Actually, there are some other related interesting things. For example, when you talk about level 9, you can see this corresponds to system's self-consciousness in a sense. Okay, it only sense if a sense is internal activity, it only see the top or the most active concepts. It's not going to know everything about itself. Okay. Anyway, when the system is running, you can see. By the way, this is a very dangerous button. Okay. If you click this one, is continue run. Okay. You see, this is a single step, and this one I just do it for demo, just to show you it can happen. But you cannot really follow the system in this way, okay? Just because it runs too fast. You see, but you can click off. Is basically you stop the display, but the system is continue running in the background. Okay, so this is a snapshot at a certain moment, and if you click on, it will go back. Okay, so this is just to show this is possible. In reality, you typically do this. Especially at the beginning, okay, one step at a time. So,
how come the system keeps changing its beliefs even though there is no new information and it keeps track of the base of the evidence?
Sometimes, it depends on the combination. One thing I haven't mentioned is, you see, in this kind of simple example, you will see pretty soon there's only 2 or 3 inferences can be done, right? After that, what else are you doing? One important thing we haven't mentioned is the system constantly builds new concepts, which is beyond the level 1 stuff. Okay? So in that sense, even if you're not giving the system anything new, it can still produce stuff. But some of them will be useful, some of them, or actually most of them will become useless. But at the very beginning, at the moment when you produce them, you don't really know. You kind of like leave them there let them compete and use the future experience to tell you which one you should keep. Okay? That's why you still see things going on, but in level 1, actually you shouldn't. So you see, if you go all the way to the bottom, you see that's kind of like all the things that the system produces. That's why it's not too crazy. If I pick another example.
Can you show us an example where where the rules are contradictory?
Oh, yes.
Say,
Yes.
yeah,
That's the
say,
good one.
Birds swim and birds drown. And then maybe there's some other rules say swimmers doesn't drown.
I have one for that kind of thing. Okay. But let's finish this topic. It's just sometimes you see this example, there are only 2 lines. You say, I don't want to run, but I can say 10 step. You see, it's going to produce a whole bunch of stuff. Okay, in this case, many of the concepts are not from the input. It's built by the system itself. Okay, this is the topic we're going to say much more in the next week. Okay, it just shows you that there is this kind of thing. And then what else? And this will show you the current content of the buffer. Okay, the buffer is the place, the new result will be put in, but many of them will be thrown out, and some of them will go into the memory. If you want to know what's going on there, you can take a look. This one will allow you to go into a concept. For example, you see, this is the top level picture. Okay, and this is a more detailed picture within a single concept. For example, now you want to know what the system knows about bird. You see that there are actually several windows pop up, which this one is clear. This is what we have explained a little bit. That's the task bag related to bird. Okay, that's all the active task, what the system is thinking about directly related to bird. Also, you see on different level of priority, okay, with some additional information which we don't have the time to explain now. But roughly speaking, that's, you see, all of them will have a bird in it somewhere. By definition, otherwise it will not be there. So this is one. This is another one which is kind of like related to the belief bag I mentioned. Okay? In reality, it's not, as I said, it's not implemented in that way. It's a more complicated version, but it's kind of like tell you where to get the belief about birds. Okay. They're stored in some different place. So that's this. And this will tell you the direct belief and question about that concept. Again, that you don't have anything about that for first layer. Okay. This is basically used when that node itself is a link. But then if that's the case, for example, you will see the truth value of the link. For example, say this one. Okay. If you want to look into this, in this window, you're going to see the truth value attached to that statement within the system. Okay. So that's another thing. What else? This window gave you kind of like the most complete information about what's going on. That is, if you do step by step, this window will tell you step by step. In each working cycle, that's the clock, timer, okay? Which concept, which task, which belief is selected with what priority value, what result is derived. In many situations, there's nothing can be derived because of the combination, especially for simple examples. Okay? But anyway, this is very important if you really want to do debugging or if you want to trace the reasoning system. And this will actually do it step by step, give you all the information you need. And not all the information, but a lot of information. Okay? So, what else? This will just bring up this window. If just in case you close it, you want it back, you click this one. And some of the parameters can be adjusted at runtime. Okay? I don't have many of them. I have several. For example, the forgetting rate. I told you that everything decays. All the concept priority, task priority, belief priority decays. And the decay rate, I have a default value, but it can actually be modified at runtime. Okay, I have an explanation somewhere else about what that number actually means. Okay? So you can make it slower or faster. You'll see what's going on. For now, at the current moment, that doesn't really make a lot of sense, but it just shows you this kind of thing can be done. The most common used or adjusted parameter is this. It's report silence level. This tells the system what you want to hurt. The smallest value basically means tell me everything you derived. Okay? On the other hand, if you move it to the top level, basically say that keep everything to yourself except answers to my questions. Okay? So for more complicated problem, you want to do this. Otherwise, you get way too many reports about, I get this, I got that. Usually, you don't care about those things. You just want the final answer for your question. Okay, but for debugging purposes, sometimes you really want everything, or you want something in the middle of the system. Use some kind of function to evaluate the threshold, okay, what to be reported or what not. But for now, the most common used value are the two extreme. Okay, either tell me everything or tell me nothing, but answer my question. Okay? You can have something in the middle. Basically, say only tell me important things. You get, okay, you think it's important, according to some standard. That's the parameter. Basically, you only need this one. And this, of course, give you some, related information about the system, version number, and so on. Okay. So that's basically the current demo. Of course, at the moment, it can only handle very simple problems. It cannot really handle complicated things because the control mechanism is not that mature, and also part of the control job will actually be handled by the logic itself. I already begin to mention the system have some ability to do self-control. That's level 9 stuff. So we're going to say much more about that in the next week. So in the following, I'm going to go through some simple example, okay, to explain to you if you want to play with it, where to start. And clearly, feel free to modify them just by changing the word or changing the number, everything by yourself. Okay. So let's see. I said that you may want to start with a single step because I have already tested them. If you just want to understand what's going on, you don't really need to run the demo, okay? Because this file is basically a record of the input and output. As far as you trust me, okay, this is not something I typed in to just fool you. You can just read this file itself, okay? Let's see what's going on in this file. This is level 1, okay? Revision. I tell the system bird is a swimmer with the default truth value. And then someone or myself at a later moment or even in the same moment in a different sentence tell the system, you see, it's kind of like unlikely or probably not, okay, a type of swimmer with a slightly lower confidence value. Then what the system get is a compromise of the two, okay? This one is still quite positive because the default value is much higher than this value. And the confidence level is higher than both of the premise. As I said, this is a summary, right? So this is revision example. Deduction example, you see bird is a type of animal, robin is a kind of bird, and robin is a type of animal that can be derived. You think, yeah, it actually only take one step, but why 5 working cycles? As I said, the system doesn't necessarily know which tool to pick. Okay, it kind of like, as I said, using a probabilistic priority queue, so it may happen to pick something, a concept which doesn't really produce anything useful. Okay, if you trace the system step by step, you will see that only in step number 5, it picked the concept bird and picked this and this. One is a task, the other one is a belief. Which is which doesn't really matter too much. Okay, and get this conclusion. Okay. As far as this number is small, whether it's 5 or 4, usually it doesn't really matter. It's just something can be derived. And this is an abduction example, induction. Also, by the way, you can also change the priority value. Okay, you see everything coming in. If you don't say anything, it gets a default priority. Okay. But you can change the default priority. You can say that this is more important than that, even though I tell you both of them. Okay. So just make things simple. I'm not going to talk about that at the moment. So each of them, you see, is about a rule covered in layer 1. And overall, layer 1 have 7 rules. We covered, talked about more about 4 of them, but there are a couple of others. Also, this is about the choice rule, which is used to answer questions. You see, this is a question, right? And this answer, you see, clearly, trivially answer this question so that you are going to get an answer. And this is a question with a variable term in it. Everything starts with a question mark is a variable. Okay? Typically followed either by a letter or by a number. Actually, within the system is always by a number. But on the user interface, you can use a letter to separate. For example, what if you have 2 variables in the same sentence? Okay, you can say X and Y. And then this is backward inference. That is, if you know bird is a type of swimmer and you're looking for a swimmer, and then this one itself, of course, already provide an answer. But at the same time, the system also produces 2 derived questions. Okay, it's kind of like ask itself. What is the type of bird and what is the type of bird? The rule, as I said, is if either of them get answered or both of them get answered, the answer of this plus this one will provide the answer for this. Okay, that's where how the system produces sub-task from a given task or sub-question from a given question. Okay. And clearly, this is the simplest case. Later, we will see more complicated case. So that's one file. This one gives you more detail, but it's a little bit boring. Okay. A more interesting file is this. It's a multiple step inference. Okay. And that's the one that can answer some more complicated questions. So I have a file which picks some of them. Once again, you can use copy and paste to actually try it. But since this file already gave you the complete input and output process, you don't have to confirm it. Instead, you see, for each of the problem, I give you the input, which is the part that you can just do copy and paste, okay, into the system. And I tell you that this is what the system will show, at least the current version. So you don't really have to run it to see the results. So you can just read this to see what's going on. This example shows what if you have more than one candidate. Okay, you'll see that I tell the system Robin is type of bird with the default truth value, and after a while I told it swan is also a type of bird, penguin is a type of bird, both of them with something different from the default. Okay, you see this one, the frequency is still positive, completely positive, but confidence is slightly lower than the default 0.9. And this one, we say penguin, well, it's not a typical bird. It's some of the property of a bird penguin doesn't have, so I say it's 0.8 in terms of inheritance. But the confidence level is relatively higher because for some reason, it's kind of like I know more about penguin. Okay, just let's assume that happened to be the case. Then after a while, I ask the system, what is a good example of a bird? Or tell me a bird. Okay, or actually speaking, is a type of bird. Then give it some time to think about. You'll see this is the dialogue. This part is basically repeat what we have with all the default value filled in and also the evidential base recorded. Then that's what the system tell me. Actually, the first one it found is a compound concept, okay, which looks confusing, but we are going to talk about that in the future. That's just something the system made up by itself. But then later, it actually found this penguin. You'll see, because it's a probabilistic priority queue, you actually have no control unless you check it very carefully about which answer it will pick up first. Okay? It's give you the feeling that it's kind of like random. Even in reality, there is nothing random at all. Everything is explained. It's pure deterministic. It's just the observer usually don't have all the information. Okay? So let's just say that given this situation, it happened to be the penguin that get picked up first. But actually, if you change those numbers, they may pick up something else. Okay? But anyway, the choice rule remains the same. The choice rule, if you calculate, you see for this one, according to my explanation, it will use the expectation value to decide which answer is better. Okay? So even though it pick up this one first, it changes answer later and later. Okay? Just because if you check the truth value function, this will give you the highest expectation. What if the system happened to pick up Robin first? Is the answer. Well, if that's the case, I will stay with this one. Because all the other candidates, even if we find it later, is not as good as the one that already reported before. Okay? So this one I will show you as an example about what I said, this anytime behavior, and also if the system is really complicated with a lot of information about birds, you really have no idea. Neither the observer or the system itself will have an idea about which answer is actually the final answer. Actually, in this system, logically speaking, there's no such as concept as a final answer. But there is a concept of a better answer. Okay? That's what the choice rule decides. Okay? So this is one case. And here I have a brief explanation about what's going on. And this is about contradiction. Okay, let's see. This one is a little bit beyond what we have covered because we haven't talked about this. Okay, but that's actually that's the negation symbol. When you say it is not the case, actually there are at least two ways to say it. One way is I said already, you put a 0 as a truth value. Okay, that's negation. Or you can explicitly use the negation sign, which is this double minus sign. The accurate definition of this, you will have to wait until level 5. Okay? In level 5, you see you are going to take the sentence itself as a term, and the negation of it is a compound term. Okay? But you can understand that with no problem. So you'll see what it means. I tell you that coffee is a type of beverage. I tell the system, and Java is a type of coffee, and then I tell it Java is not a type of coffee. Okay, it's a kind of explicit contradiction. I try to get the system confused and see what will happen. Okay, and this clearly is using the information that the Java, the word can be interpreted in different meaning, and under some interpretation it's coffee, and some other interpretation is not. And then what if I'm mixing different interpretation together? The interesting thing about this is the traditional logic system. You see that as soon as you give it this both A and not A into the system, then what will happen?
Derive anything.
Oh yeah. Right? That's called implication paradox, right? From a contradiction as premise, you can derive any conclusion. This, if you check the truth table of predicate calculus, is true. It's always true, no matter what B is or what A is. Okay? That's a major problem in classical logic. That's the whole branch of so-called paraconsistent logic was developed for, just to avoid this trouble. Okay? This example, I show you this trouble is not in the system. What the system does is quite reasonable. That is, after you give it a contradiction plus something else, you ask it 3 questions. Okay? Then let's see what the system will tell you. At least first is not crash. Okay? Many reasoning systems, wherever you put this in, it will either directly crash or reject it. Say that's not allowed. Okay? Many reasoning systems, actually most of them, either demand consistency and put the burden on the shoulder of the user. Okay? If you give me a contradiction, that's your trouble, your mistake. Or the system try to check it wherever it's found, it will reject the whole problem, or somehow separate the two into two, what they call context, and try to do it locally. Okay, I'm not happy with any of them. Okay, anyway, let's see what this system does. If you ask it whether it's coffee or not, of course it will be confused. Okay, you tell me yes, you also tell me no. How can I know? Okay, I would say 50-50 because they are equally strong. This one, you see, have the same level of confidence. One say yes, one say no. Of course, I will have to take the middle point. Okay, and this one have a higher confidence because it's a summary of the two. Nothing special. I also see where it comes from. It's from this line, this one. And then you ask it whether tea is a type of beverage. You wait for a while. There is no answer. Why? Because tea was never mentioned before. Okay? So basically the system, no answer basically means I don't know. The system, the current design does not include I don't know. It's just silence. Okay? Of course, it can be easily changed. Say that if you don't derive anything within a certain amount of time, you just say I don't know. Then if you find an answer, you change your mind. You can do it that way. Currently, there is no answer. But why I bother to include this? Just to show you it doesn't make this mistake. If following this logic, it should say yes, right? Because from a contradiction, you believe everything, or at least, well, even if you believe it to a degree, you should be able to say yes to a degree. But here it says nothing because what makes this system different is a contradiction still causes trouble. That's for sure, just like us. But this trouble is a local trouble. Okay, the system becomes uncertain about whether this is the case. But it doesn't have a global disaster, mess up everything else. Okay, you see for this question, it still have no answer. For this question, whether coffee is a beverage, that's something mentioned here, and you will still report that is the answer. You'll see the contradiction have no impact on those two questions. You only have impact on the question you directly ask about the contradicting evidence. Okay, I believe that's a much better answer or solution than what have been proposed before.
Say this again. What are these numbers for lines? Why the 10, then 1 again?
Some of them are decided here by me. It's just how much time you allow the system to think, or is the pace of your input. Whether you dump everything together or you kind of speak slowly so that give the system some time to process after each line. It's up to you. But for some of the questions, the system is sensitive to that. Just like us. Okay, if I talk very fast, there is no time for you to think about what I have been talking. So,
Do later versions of NARS give NARS the perception of time, so sort of work out how long the user likes to wait, sort of thing? Okay.
Can you represent the context of this belief? Say you have another rule saying Java is beverage, and then another rule says Java is a programming language, and then maybe somehow you will be able to infer if you see Java is a beverage and Java is coffee happening at the same time very often, then you would be able to associate these two rules. And then if you see Java is a programming language and Java is not coffee happening at the same time many times, then you will be able to associate these two rules. Does this happen?
yes, but not at this level. This level is a highly simplified situation. In the future, actually, to actually handle the ambiguity of concepts, there are actually several mechanisms. One mechanism is another level of map. You see, the Java example, the confusion is not in the concept level, it's in the word level. It's the word Java actually corresponds to two different concepts within the system. Okay, so in reality, that kind of ambiguity is actually handled as a graphical, the natural language interface. Okay, here I just simplify the thing. I just say this. Another thing is, if a concept is actually highly context dependent, within the system, it will actually be represented not as one concept, actually as two separate concepts, but they may inherit from a common parent. Okay? So that the context in that situation will be explicitly remembered or represented as part of the term itself, as a structure.
So you have a hierarchical structure
Yes.
of this concept.
Yes. So that's a second thing. A third factor is context also is implied by the priority value. So that if I mention Java, you think about, say, 5 different things in one context. In a different context, if I activate this one, all those 5 will become forgotten. Instead, this one will be taken into consideration. And that will also change the meaning of a concept. Okay? For that, we are going to say much more again in next week. But here,
can this system deal with graphs with that have loops or something? Like, what if you add x is a y, y is an x, and then you add? It's not the case that x is a y.
yeah, it can handle that kind of thing. But there are several things that may happen. It's not going to loop indefinitely because of the mechanism I mentioned. Okay, a conclusion will not be reused with the premise. But if these two things come from different source, you tell me x is y and she tell me y is x, then the system at least is going to derive this. That is, x and y are similar to each other. But that's a copular we haven't introduced. That's something to be introduced in the second layer. Yes. Yeah. Something like that will be handled.
Can you represent behavior in this?
Yes. Wait until layer 8. Okay. I have to keep saying that because layer 1, later you will see, it's kind of trivial because it only contains a teeny tiny bit of the whole thing. But this gives you the foundation. That's the most important part. But everything more complicated, you will have to wait. Otherwise, I don't have so many layers. That's okay. But Whenever you mention that, I will just tell you which layer. Okay, details will be covered in the future.
Do you have a simple example that's built around a logic puzzle?
Actually, I have several of them, but yeah, let me mention one, but I'm not going to fully answer that. That's the one I mentioned before. That's one of the well-known logic puzzle. I don't know what do you mean by logic puzzle. Is the puzzle played by children or puzzle that's solved by logicians?
Like Einstein's puzzle. Do you know that one?
I don't.
There's many houses and residents of each house, and the many attributes of each resident is given, but some are unknown, and you have to derive the output, and it's somewhat complicated.
Yeah, I will leave that thing for the future. But I want to mention one puzzle which is already related to what we have discussed. It's the so-called Raven's paradox. It comes from the study about induction or confirmation. That is, we know all the observations are concrete. How can we get general opinions or conclusions like ravens are black? Okay, ravens are black traditionally in fourth-order predicate calculus is represented as for every x, if x is a raven, then it is black. Right? If you, from your first order predicate calculus course, that's what you are taught. How to derive, or actually they don't even talk about derive. Many people say it's to derive it is impossible, but to confirm it to a degree is possible. That is, what gave you positive evidence to believe this thing stronger? Well, one opinion say, for something of this pattern, okay, if you see a constant which satisfies both the premise and the conclusion, is positive evidence or is confirming evidence. In other words, if you see a black raven, you should believe ravens are black stronger. It sounds like common sense, right? But the trouble is, this thing is logically equivalent to the proposition for every x, if x is not black, then x is not raven. Right? A is B is equivalent to not B is not A. Okay, that's fourth order predicate calculus or propositional logic. But if that's the case, this thing is not black, right? Also, it's not raven, right? That is positive evidence to the sentence according to the pattern we just generalized. But this one is equivalent to this. So as soon as I show you this, your belief about black, ravens are black should become stronger, right? Think about it. Okay, we can talk about it later. It's very simple. It's surprisingly simple. Okay?
It's more about my previous question. So if you have x implies y, or is there a y with confidence 1 and y implies x?
Oh, you don't have confidence 1.
Well, with the
Very high confidence, yes.
with the same number, and then you add. Okay, and then you add not x implies y with the same confidence. what would be the result? I don't see it.
I don't know. We can try. That's the easiest way to solve it. Okay, we have a working system. Okay, so I don't want you to think I only have built-in, canned examples. We just need to be careful about the grammar without putting any extra symbol or missing any symbol. Let's just use the default confidence just to make things simple. Then what you want to negate, which one? Just this. Okay. How about this? Make sure the memory is indeed empty. Oh, it already is. The parentheses match each other, yes. And let's run and let it report everything. Yeah, sometimes if you forget that, it may actually produce something. I just didn't report. And let's run for a while. Let's see what will happen. Yeah, there are a couple of other things derived which we're not interested. We just want to get that one. It's a compromise. Yeah, and the other direction doesn't really matter in this example. Whether that makes sense or not, whether it's justified or not, we can think about that. But anyway, that's why I want to do the demo, right? So if you have a question for now, especially for all the guys with laptop with you, you can have a try first, okay? You don't have to always ask me, even though I'm glad to answer them. But if we don't have the time, you can actually try the simple examples by yourself and see whether the answer match your intuition or expectation or not. Okay? So let me quickly finish all I think that should be finished today. So yeah, we talked about this contradiction thing, and the following one is also similar. But it contains something in level 2, so we are going to talk about that example before in the next time. But again, it shows you that the system, some of the belief of the system are either to be modified, some of them are harder, okay, because of where they come from, because of their confidence level and so on. So that's what this one does. Yeah, this one also contains a symbol we haven't covered. Let's see this. This is interesting. Very simple. Okay, what is covered is induction and revision. Reset the memory. I begin by asking the system 2 questions without telling it anything. Okay? I ask it whether bird can swim or whether swimmers are birds. Clearly, you cannot expect any answer. But the difference is, you think about traditional AI system or conventional computer system. If you ask it a question beyond its current knowledge scope, what do you get? Either nothing, or the system crash, say the command doesn't exist, or it rejects the question, say I don't know how to handle that. Anyway, the problem is gone. Okay, in NARS, according to what I told you, you can guess what's going on. Those 2 questions doesn't get answered, but the task still get pending in the system. Okay, it will exist for a while. Then I begin to tell it related stuff. I tell it that swan is a bird and can swim. According to the definition, now you should know that this one gives evidence, positive evidence, for both questions. Okay, and then since those questions are still active, after you put this in, after a while, the system realizes that it can give you an answer for the previous question, which has been pending over time. But the confidence is not very high because this is induction, one piece of evidence. Okay, but after that, if you continue to tell it more, it will continue to revise its answer. And you see this one, this pair have a higher confidence because it's based on more evidence.
Is it doing it automatically?
You see, I didn't ask the system anything, right? I also.
It keeps this question in the back
Yeah.
and revisiting it during.
As far as the priority is still high enough. Okay. Of course, if you wait for a long time, of course, it will be gone because of the forgetting mechanism. If it's not very far, it will be there. But so far, you see still positive evidence, still symmetric. But now I begin to tell it a piece of negative evidence. I tell it that crow is a bird, but it cannot swim. Okay? And then you'll see only one answer get revised. It's this one. Because crow is a bird, it cannot swim, is the negative evidence for birds swim. So this one get decreased. How about the other thing? The other thing remains the same. It doesn't change that answer because that thing, crow is irrelevant for that hypothesis. That conclusion says swimmers are birds. You give me something which is not a swimmer. Whether it's a bird or not, it doesn't matter, okay, for whether swimmers are birds. Actually, this is related to this. Part of the problem, I'm not going to spend the whole time to talk about all the details. Just part of the problem is because traditional logic doesn't really have the way to tell you something is irrelevant to a hypothesis. Okay, and this thing is irrelevant to whether ravens are black or not. Okay, in this system, it can handle that. Question?
This is really, really cool. But if you turn it into an AGI, you're going to be feeding, you make a robot, it's got two little eyes and an arm and all that sort of stuff. You're going to be feeding input into NARS. How do you, because what you're doing here is feeding high-level concepts into it already and pulling high-level concepts out. How are you going to get robotic input or robotic output out of this sort of thing?
Layer 8. Wait.
Right, I'm happy with that.
You see, I have an answer for every question. You just have to wait. Anyway, so this one, if you check it carefully, you will see this is actually nothing but statistics. Okay, this frequency is what is 2/3. I see 3 examples, 2 positive, 1 negative. Okay, and this is basically for 3. This is for 2. This is for 1. If the evidence comes with the default truth value. But the difference between this one and statistics in one aspect is statistics typically require all the data to come in at the very beginning. Then run an algorithm, give you an answer, done. This thing is incremental. Okay? So your new information or data can come into the system at any moment, and the system doesn't go back to all the raw data and redo the calculation. Instead, it uses this to modify its previous belief. And also, this result is different from Bayesian network conditioning. Okay, if we have the time, we can do that. But you can think about how to use a Bayesian network to get the same consequence or similar consequence. There are all kinds of problems. Okay? And the last question I want to show you is also related to the previous discussion about when can the system decide which rule to use. It's data-driven. Okay, let's see this example. I tell it swan is a kind of bird, swan is a swimmer. I put this after the previous example just because this part is basically the same thing. Okay? with slightly different order. I gave it a question. The question is whether bird can swim or not. I give it 2 pieces of positive evidence for that. Actually, one is before the question is asked, one is after. You will see that within the system, if everything goes normally, and there's nothing completely forgotten or ignored, there will be 2 pieces of information for the conclusion that bird can swim. Okay, then this is something to be introduced in layer 2, which, roughly speaking, in layer 1, every concept is a noun. In layer 2, we can begin to introduce things like correspond to adjective in English. It's a property. Okay. So that you put this around the adjective, you turn it into a noun, roughly speaking. Okay. So for now, we just take this as a term. So this basically say that bird has feature as a property, and also we know robin has that property. So by abduction, if you check the rule, okay, by abduction from this tool, it can derive that robin is a type of bird. So if robin is a type of bird, a bird can swim, they can derive robin can swim. So it will eventually be able to answer this question. But if you check the process step by step, you'll see this simple question require deduction, abduction, induction, revision, all mixed together. Okay? So that's kind of like the best example to show you what this system can do, even on a very simple problem, which traditional AI, if we do deduction, it's deduction only. Induction, well, there is inductive logic, which do induction only. Or you will have to tell it explicitly which is which. In this one, you just send the system knowledge. Which rule will be used will completely be determined by what knowledge is available and what knowledge is recorded by the control mechanism at the moment. And furthermore, the conclusion of one rule will be used by another rule as a premise and so on. So in this way, all the different type of inference are naturally combined in the whole reasoning process. Okay. Also, it shows you that you don't need to give it an algorithm for a long chain of inference to say what's the order of the rule. Okay. It's not random, of course, but it's determined by, you can only say, by the current context. Okay. So that's kind of like step-by-step process. And if you follow it step by step, you check the combination, you will see which rule is used. But usually you don't care. You just give it the premise, you say, what's the conclusion? Okay. And a couple of more things, more complicated, this is about compound term. Again, we're going to talk about that in the next week. So by now, we have a complete description about layer 1. Okay. Then in the next week, I'm going to introduce each of the layers, concentrate on the logic part, that is new grammar rule, new inference rule. But also I'm going to mention something about the control mechanism, the memory structure, of course, there also need to be modified accordingly. Okay. So then after the next 3 lectures, you will have a much better idea about the whole system, even though many details will have to be left out. Okay, that's all for today.